applications of extrema are functions of two variables. In Calc 1, we talked about max-min problems. Now we're going to talk about the same thing, but in 3 dimensions. And the first problem we're going to do is, suppose you have this surface, and you want to know what's the closest point on the surface to the point 0, 0, 0. In Calc 1, maybe you were given y is equal to x squared, which looks like this, and you were given a point, maybe 2, 0, this point right here, and you wanted to know the closest point to the curve. And well, you call that arbitrary point xy, and you computed the distance. It was x minus 2 squared plus y minus 0 squared. 2 and 0 came from the point, and then you eliminated one of the variables. You eliminated y. You said that y was x squared. And you minimized d. Well, we have the same analogy here. Let's first solve for z. Bring the 2x and this 3y over. So z is 12 minus 2x minus 3y. So let's call s the distance. S is going to be x minus 0 squared plus y minus 0 squared plus z, which is 12 minus 2x minus 3y minus 0 squared, the square root. Now, we want to minimize s. When you have a square root, if you want the least, want the min, you let what's underneath the square root sign be the least. That is, s squared is x squared plus y squared plus 12 minus 2x minus 3y all squared. Except no square root, sorry. That's what s squared equals. Minimizing s squared is the same as minimizing s. We want what's underneath the square root sign to be the least. That's when s squared is min. So here is the difference in Calc 3. We need to find the partials and set them equal to 0. S squared sub x. Don't ask me why I wrote it that way. With respect to x squared, I want to take the partial with respect to x. This is a function of x, there's its partial. Plus, that's not a function of x, hence it's a constant, its derivative is 0. Plus, this is a function of x to a power. So you use a general power rule. You bring the power down, you keep what's inside the brackets the same, make the new power 1 less, and then multiply by the derivative of what's inside. And you will get, now I hope you see that between here and here, you can factor out a 2. So you get x minus 2 times this. That is, I'm distributing the 2 now. Not this 2. Those 2's have been factored out. I'm distributing the 2 here. Or negative 2. I get negative 24 plus 4x plus 6y. And combining like terms, x plus 4x is 5x plus 6y minus 24. That is s squared x. I'm going to write that on the bottom because I'm going to erase to find s squared y. Since s squared x on the bottom is a function of x and y, I can't solve that equation alone for 0. Because I want to set these two equations equal to 0, s squared x and s squared y. Okay, s squared y. This is not a function of y, so the derivative is 0. This is a function of y. Its partial is 2y plus this here is a function of y. There's a y term. Bring down the power. Keep the inside the same. Make the new power 1 less, which is 1, which you don't have to write. Times it by the derivative of what's inside with respect to x. Only the 3y with respect to y. Only the 3y is a y function, and its partial is negative 3. Now, I can factor out a 2, and I get y, and negative 3 times 12, negative 3 times 2x, negative 3 times negative 3y is positive 9y. Combining like terms, like y plus 9y, that's 10y, I'll say, okay, plus 6x minus 36. And I say, oh, I can factor out another number. I can factor out a 2 again. I can factor out a 2 from this. So when I factor out the 2, I get 5y plus 3x minus 18. And this here is s squared y, and I want to set it equal to 0. Now, if this times that is 0, it must be that's 0. It certainly isn't the 4 that equals 0. 4 equals 4. It doesn't equal 5. It doesn't equal negative 4. 4 is identically 0. Same thing for the bottom. I'm pretty sure there was a 2 that should have been in the front. If this times that is 0, it's the that happens to be the 0. So I need to solve this system of equations for x and y. And once I do that, I have the critical point. And rather than using the d function to figure out if it's a max or a min, I mean, just look at it. You have x squared plus y squared plus 12 minus 2x minus 3y squared. If x and y get bigger and bigger and bigger and bigger, well, x squared versus 2x, or negative 2x, x squared will be much, much bigger. Y, that is x squared plus y squared will just grow so big. Well, actually, you know what? This here is the same as positive 2x, positive 3y, take away 12 squared. That is, you're just taking away 12. When x is really, 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 x and y are really, really amazingly big, you can actually just think of ignoring the 12. This just gets bigger and bigger and bigger. If x and y gets bigger and x and y get bigger, it's just growing without bound. The power is 2, not 12. That is not the critical point that we're about to find will not be a max. Okay, because there is no max. It grows without bound. Okay, I'm going to write down the top equation, except I'm going to write x first. And I'm going to bring the negative 18 to the other side with positive 18. The second equation, I'm just going to, well, I'm going to do the same thing with the constant. I'm going to bring it to the other side. Now I solved this. I want to get the numbers in front of, say, x to be the same. The first or common multiple is 15. So I'm going to multiply the first line by 5, and I'll get 15x plus 25y is equal to 90. I'll multiply the first equation by 3, because that gives me 15x's plus 18y equals 72. And I do little subtraction. I get 7y is 18. So y is 18 divided by 7. And then I'll find x. I know that 3x is using the first equation on top. 3x plus 5y is equal to 18. Now, maybe we can be slick this way. Let's bring this to the other side. So the other side has 118 minus 5/7 of 18. 1 minus 5/7 is 2/7. So we have 2/7 of 18, which is 36 over 7. Why do I like that? Because I didn't have to multiply this by 7. I wasn't looking forward to that. Okay. So you have that 3x is equal to 36 over 7. It's very, very friendly to divide the left side by 3 to get x alone. It is not friendly to divide the right side by 3. I don't know why the 3 didn't come out. Okay. It's not friendly to divide the right side by 3. Well, the alternative for dividing by 3 is multiplying by the reciprocal. You really need for that to be a technique that you have and use. 3 into 36 is 12. So many students tell me, yeah, I know that, but they never use it. Okay, and there's your critical point. You have the x value, and at some point we found the y value, 18 over 7. And I guess you should really find the z value. You really should find the z value. For example, in our 2 dimensions back in Calc 1, you didn't just say what x was, you said what xy was. But now you have to say what z is. And z was equal to 12 minus 2x minus 3y. Well, everything's over 7 except the 12. The 12 is 84 over 7 minus 2x's minus 24 over 7 minus 3y's. 3 times 18 is 54 over 7. So everything's over 7. 84 minus 24 is 60, and 60 minus 54 is 6. So that's what z equals. And there's your point. That's the closest point on this surface to 0, 0, 0. That's the closest point on the surface to the point 0, 0, 0, to the origin. Suppose we were told that z was equal to x squared plus y squared, the same problem. You have the point 5, 5, 0. What's the closest point on the surface to 5, 5, 0, as opposed to 15, 5, 0? So S would be x take away 5 all squared plus y take away 5 all squared plus z, which is x squared plus y squared minus 0 all squared. Square root of that. But let's just square it. Okay, let's just square it. Okay. S squared x, function of x, not a function of x. So the derivative of that second function will be 0. You get 2 times x minus 5 plus 2 times x squared plus y squared to the first power times 2x. Now, this problem, s squared, it's symmetric between x and y's. If I interchanged x and y's, these would change, and this would just be the same. Be y squared plus x squared minus 0. It's the same. that is s squared y will be 2 times y minus 5 plus 2 times y squared plus x squared times 2y. And we want to see when this equals 0. Well, s squared x, I can factor out a 2. There it is, x minus 5. But I still have this 2x. You can think of it as being in front. And you distribute. You get plus 2x cubed plus 2x y squared. So you get 2x. Actually, let's not distribute. Now we're going to get the same exact thing for sy squared, except x's and y's get switched. Y minus 5. So I'm not looking here. I'm looking here, except I'm replacing x with y's. Plus 2y cubed plus 2y x squared. Now I want to set both of these equal to 0. They don't equal 0. If it was me, I'd take a point off if you said they equal 0. Because they don't. That's not true. First thing I would do is I divide both sides by 2. 0 over 2 being the second side, which is 0. I divided both equations by 2 on both sides. So basically, I want to see when these things equal 0. What is the value of x and y that make these two equations equal to 0? Okay. What I'm thinking of is first, think of the negative 5 going to the other side. Or maybe not. Maybe that's premature. Let us multiply the first equation by y, the second equation by x. The reason I don't want to bring the 5 over is once I multiply it by x, it's no longer by y, is no longer a constant. I'm multiplying by y. I'm multiplying by y. 0 times y is 0. The second equation on the bottom, I'm going to multiply it by x. I get multiplying by x. I don't keep saying that, I will forget that's what I'm doing. I'm multiplying by x. Okay. Now, if I subtract these two equations, those two are the same, they cancel. I have plus 2xy cubed here, and I have it here. Subtraction kills that off, and subtraction kills that off. And what I'm left with is negative 5y minus negative 5x. That means plus 5x equals 0. Dividing by negative 5, I get y minus x is 0. That is, y equals x. When y equals x, that's the solution to the equation. And please remember that z was x squared plus y squared. So, if I let x be 1, y is the same as x, and z would be 1 squared plus 1 squared, which is 2. And that's the closest point. That's the closest point on the curve to the point 550. The just let x be 1. And y being x, y would also equal 1. Now, suppose you have that the sum of 3 numbers is 30. So you know that let x, y, and z be the 3 numbers. So the sum of the 3 numbers, x, y, and z, is 30. And you want to maximize the product. You want to maximize p, the product of these 3 numbers. Okay, so what you want to do is get rid of one of the variables in this top equation. I'm going to get rid of z, for example. So this is our constraint. We want to maximize p equals x, y, z, subject to the constraint x plus y plus z is 30. So bringing the x and y to the other side, it's negative x minus y. So p, we reduce one of the variables, just like you would have done in Calc 1. We want to minimize this equation. We want to take the derivative and set it equal to 0. But first, let's clean it up. This is 30xy minus x squared y minus xy squared. Well, p sub x, in the first term, 30y is a constant, times the derivative of x is just a constant, 30y minus. The derivative of x squared is 2x times the constant, minus a constant times x, the derivative is just minus the constant. That's p sub x. P sub y. Now look at p. Is it symmetrical between x and y? If I interchange x and y, that is right now, that's p of xy. What's p of yx? That is wherever you see x, put y, wherever you see y, put x. This will give me yx times 30 minus y minus x. But that is p of xy. That is p of xy. That is, the partials will be symmetrical. Just interchange x and y. Yx is xy minus x squared as opposed to equal x squared. And we want to set both of these equal to 0 and solve. For the first equation, I'm going to multiply by x. That gives me 30xy minus 2x squared y minus xy squared. In the second equation, I'll multiply by y. The only reason I'm doing that is because upon subtraction, I see that canceling out. And I'm hoping everything else works out well. Minus x squared y. And remember, both of these equal to 0, because 0 times x is equal to 0. The right side, we were always setting it equal to 0. So now when I subtract, I get negative 2x squared y plus I really don't see this working out, but I do see another way out. How about from this first equation, p sub x, we factor out y. We factor out y. We get 30 minus 2x minus y is 0. And in the second equation, we factor out x. We get 30 minus 2y minus x is 0. Now, I should have mentioned the instructions have always been that the variables are positive. x, y, and z are all greater than 0. X is bigger than 0, y is bigger than 0, and z is bigger than 0. That is, y is not 0. Times this is 0. That means that this must be the 0. Since x is not 0, you multiply it by this and you do get 0. This must be the 0. So divide both sides in the first equation by y. The right side will still be 0. And in the second equation, divide by x. Okay, here are the two equations. Now, I don't know if it would have been able to be done, but it seems like it would have been a much harder problem if they didn't tell us that x, y, and z were positive. That was true in the last problem as well. So, we want to solve this. I'll bring these terms over to the other side, because they're positives. 2x plus y is 30. And I'll write x first. X plus 2y is 30 from the second equation. And I will double the second equation, the first equation. I'll multiply by 2. And I get 4x. That way, the numbers in front of the y's will both be 2. 4x plus 2y is 60. And x plus 2y is still 30. And then when I subtract, this will cancel. And I get 3x is 30, so x is 10. And using, say, the second equation, x plus 2y is 30. If x is 10, 10 plus 20 gives me 30. 2y must be 20. That means y must be 10. Okay. And so now we have x and y is 10. But we also knew that the sum of these three numbers was 30. Well, if this is 10, and this is 10, and the sum is 30, that must also be 10. Z must be 10. 10 plus 10 plus 10 gives me 30. So Z is 10. So the final answer is x is 10, y is 10, and z is 10. You have the sum. You have the sum, and you want to maximize the product x, y, z. Just divide by 3. Just divide by 3. Let each of these be 10. 10 times 10 is 100, times 10 is 1,000. That is the max product. So if you're going to build a cage, and your constraint was that x plus y plus z should be 0, I meant to say 30 feet. Well then, what you should do is you should build a 10 foot by 10 foot by 10 foot cage. Cube. Suppose they tell you that the sum of three numbers is 30, and you want the sum of squares to be min. X plus y plus z is 30, but this time the sum of their squares. The sum of the squares. X squared, well here are the squares, there's the sum. And you want to minimize that. You want to minimize this. So, you need to get rid of one of the variables. You get rid of, say, z. You don't have to, but you could. Z is 30 minus x minus y, just like it was in the last equation. And then you plug that into the equation that what's called the objective equation. the one that you want to minimize in this case, plus z, 30 minus x minus y squared. Now you can square that, but I wouldn't. But you could. That way you won't have to involve the power rule when we take a derivative right now. S of x is 2x from this, 0 from that, plus, bring down the power, keep the inside the same, make the new power 1 less, which is 1, and then multiply by the derivative of what's inside with respect to x, which is negative 1. That's why I have the negative there. So you can factor out a 2, that 2 and that 2, and you get x minus 30 minus a negative x is plus x minus a negative y is plus y. That is, you get 2 times 2x, x plus x, 2x, plus the y minus the 30. That's Sx. Now, when I look here, I say, oh, symmetric in terms of x and y. So I can just read off Sy. It's 2 times 2y plus x minus 30. And what I want to do is I want to set each of these 2 equal to 0. That is, it's not the 2 that's 0, it's what we're multiplying the 2 by. So 2x plus y, I'll bring the 30 over, equals 30. In the second equation, I'll bring the 30 over, but I'll write x first. X plus 2y is 30. If you double the first equation to get the same numbers in front of y, you have 2y. And the second equation already has 2 y's. If you subtract, you get 3x is 30. So of course x is 10. And if this is 10 and you want to end up with 30, that must be 20. 2y must be 20. So y is 10. 2 times 10 is 20. So y is 10. And I want the sum to be 30. So z has to also be 10. And that's your solution. Alright, so that's another problem completed. Let's look at the next one. Suppose you are told that the volume of an ellipsoid, which is a football, it's this 3-dimensional ellipse. Suppose I tell you that the volume of what I'm about to write, the volume of this is, see if I remember, it's 4 pi ABC over 3. Suppose I tell you that's the volume. Now, suppose I tell you A plus B plus C is fixed. So if A plus B plus C is fixed, that is A plus B plus C is fixed. It equals to some constant. What is the max volume? If they actually asked us to show, if this is fixed, show that the ellipsoid of maximum volume is a constant. Now, keep in mind, if A, B, and C are the same, call it D. If you have x squared over D plus y squared over D, or if you prefer D squared plus z squared over D. So D equals a squared. But since a equals b, d is also b squared and d is also c squared. This is 1 multiplying everything by d. You get this. And maybe I'll say d squared. Okay, I lied. D is a squared. D is b squared. This is the equation of a sphere centered at the origin whose radius is d. I didn't want to say square root of d. So all we want to do is find the max volume given that a plus b plus c is a constant. It's fixed. It can't change. And then we'll conclude, oh, look at this, a equals b equals c. Oh, that's a sphere. A football is a sphere. It's a special type. Let me say it again. A sphere is a special type of football. Remember, this is an ellipse. If I let these get bigger, but I can keep that distance the same. I'll try my best. But instead of going from here to here, I'll go bigger. At some point, you'll get a circle. The circle is an ellipse. An ellipse is x squared over a squared plus y squared over b squared equals 1. Well, if a squared and b squared are the same, call it a squared. If a and b are the same, then you have a circle. Multiplying everything by a squared, you get a circle of radius a. A circle is an ellipse. A sphere is an ellipsoid. It's a special one. It's where a, b, and c are equal. Okay, so we want to maximize the volume. So solving, say, for c, we get that k, how about c if we're solving for c? C is nothing more than k minus a minus b. So then the volume would be, using our formula for the volume will be 4 times pi times a times b times c, which is k minus a minus b, all divided by 3. And we just want to find the partials. 4 v sub a. 4 pi over 3 is a constant. And let me multiply this out. You get 4 pi over 3 times abk minus a squared b minus ab squared. Yeah, I guess that is easier. So v sub a, the constant stays, times the derivative of this with respect to a. It's bk minus 2ab minus b squared. Question is, if I interchange a and b, do I get the same answer? 4 pi over 3. I'm looking here, and I'm going to interchange a and b. b squared a minus ba squared. Well, this is that, this is that, and this is that. Yes. So then I know what v sub b is. Just interchange a and b over here. And you get ak minus 2ba, which I'll write as 2ab, minus a squared. And we want to set these equal to 0. We want to set these equal to 0. Well, then it's not the 4 pi over 3 that equals 0. It must be this that's 0. It must be this that equals 0. So we have bk minus 2ab minus b squared equals 0. And we have ak minus 2ab minus a squared is equal to good old 0. Now, if I just subtracting as I see this leaving, I get b minus a times k minus b squared minus a squared. And this is 0. I can factor this last equation. I can factor this. It's the difference of squares. It's b minus a times b plus a. And then I can factor out the b minus a. And what I'm left over with is what I did underline. The k, the minus, the b plus a. The k minus b plus a in brackets. And this is still 0. Now, in this problem, I didn't really have to say, oh, the variables, the constants a, b, and c are positive. It's understood from the get-go that they're positive. So, okay. So now let me erase some of this. So actually, I didn't mean to say that last statement, although it is true. So if this last product is 0, that either means that this is 0, which means b is a, or this is 0. That is k is equal to a plus b. But that can't be, because we said that k was equal to a plus b plus c. Now, if k just equals this, that would mean c is 0. But that can't be, because there it is. A, b, and c are positive. They're definitely not 0. You can't be dividing z squared by 0 squared. So this is not true. So now we're almost done. We have a equals b. I just have to show that it equals c as well. Well, I mean, from here, we know that c is k minus a minus b. But b is really a. So it's k minus 2 a's. Okay, let us take this equation right here. Let us take this equation right here. AK minus 2AB minus A squared is 0. So AK equals 2AB minus A squared. Dividing both sides by A, K is 2A minus A. 2b minus a. This should be minus, sorry. Actually, they both should be plus when I bring them to the other side. But remember, we learned that b was a. So this is really 2a. So k is 2a plus a. K is really 3a, okay? And then we do what I just did down here, and with the knowledge that k is 3a, well, when you take away 2a, you get a. That is c is a. C is a. So we did conclude that a equals b equals c, which implies that this is the equation of a sphere. That finishes that problem. Let us do one more. Okay, here the algebra was getting in the way. Now, in 2 dimensions, if you had a fixed perimeter and you wanted to make a rectangle, it was going to be a square. Now, we have a rectangular box. And we want to show that the rectangular box of a given volume and minimum surface area is a cube. Show that the rectangular box of a given volume and minimum surface area, we want a min surface area, is just a cube. So we're told, so we're given that the volume is fixed. Length times width times height. This is a K. Now, if you think about what the surface area is, let me draw a nice cube, well, a rectangular box. And you have the top and you have the bottom. Those areas are going to be the same. It's length times width. And up and down, that's the height. So the bottom is just going to be LW. You have 2 of those. Plus the right side and the left side. It's L times H. It's L times H. Same thing over here. This is L and this is H. So you have 2 LH. I backed it out to 2. Now you have the front and you have the back. Well, the front is W by H. W by H. Same for the back. Doesn't look the same length, but that's W and that's H. Plus WH. That's the surface area. Okay, and we want to minimize the surface area, given that we have a fixed volume. So in other words, you need to build some kind of a rectangular box with a fixed volume. But you know, you're going to build it. You're going to go and you're going to get this wall of this size and this wall of that size. You're going to get 6 walls and you're going to nail them together and you can say, look at my wonderful rectangular box. But all you care about is how much can go inside. You're going to put something very malleable inside. You're going to put maybe water inside. Okay? And the water doesn't care about the size of the wall. It just cares about how much, doesn't care about the surface area. Just cares about how much space is inside. So you want to minimize the cost. You want to get the cheapest, you want to pay the cheapest for these 6 walls. Okay? So you want to minimize the surface area. Okay. So you want to minimize this subject to this constraint. You need to eliminate one of the variables. From the first equation, we can solve for H. And H is equal to K over LW. And then we just plug that into the second equation, which we want to minimize. S is equal to 2 times LW plus L times H. And personally, that's how I write H from now on, plus W times H. Okay. S is equal to 2 times LW plus the L's cancel out. You get K over W plus the W's cancel out. You get K over L. And we want to find the partials. S of L. Well, the 2 stays. The derivative of L times the constant is just the constant, plus the derivative of just the constant is 0, plus the derivative of K over L with respect to L is negative K over L squared. That's SL. Now, SW. Well, look at S. If you interchange L and W, you get the same answer. You interchange these, you get the same answer. You interchange W and L, you get plus those two terms. So it's just 2 times L minus K over W squared. And you want to set them equal to 0. You want to set the partials equal to 0. Now, it's 2 times that equals 0. It's not the 2 that equals 0. It must be what's inside the brackets. Well, if a subtraction is 0, that means those two things are equal to one another. 2 times this is 0. It must be what's in the brackets that is 0. It certainly isn't the 2 that equals 0. And if this minus that is 0, that means this equals that. K over W squared. Okay, so we have these two equations and we want to solve for L and K. So let me start working up here. We know that, well, L is equal to K divided by W squared. But that's another way of writing W. So it's K squared over L squared squared. That is, it's K L squared over L squared squared is L to the 4th, excuse me, over K squared, killing off the K top and bottom, we get L to the 4th over K. That's what L is equal to. L is equal to L to the 4th over K. So KL equals L to the 4th. KL equals L to the 4th. Dividing both sides by K, I meant to say L, we now know that K is L cubed. K is L cubed. So we know this. We know this. We know W is K over L squared. And that tells us that W equals L, which is just what we wanted. Okay, now we come back to the left, and we remembered that we solved for H at some point. H is K, which is L cubed. K is L cubed divided by LW. Oops, typo over here. L cubed over L squared is L. We have that W is L. So L times W. L times W. W is just L. Well, L cubed over L squared is L. So we concluded that H equals L and W equals L. That means LW times H is L times L times L, which is L cubed. The volume is going to be when all three sides are the same. Okay, that completes this section. Good luck with it. Work out a lot of problems. They're all doable.